In the first part of this question, we shall prove that the Snell martingale of H is, the Snell envelope of H is a martingale. Since M is a martingale and H is convex, Jensen's inequality gives that capital H, which is H of M, is a submartingale. That's a very useful property. Since H is adapted and the expectation of Z given Ft is Ft measurable by definition of the conditional expectation, Z is also adapted because at any time t, Z either takes a value of H or it takes the value of this conditional expectation, and both of those are Ft measurable. Since H is integrable by assumption, so is Z. It remains for us to check the martingale property. So we mentioned already that H is a submartingale. And from this it follows that the expectation of Z at time capital T, given capital T minus 1, equals the expectation, by definition, of H at M at capital T, which is greater or equal HM at time T minus 1. Thus, Z at time capital T minus 1, by definition, it's the maximum of these two, and so it is equal to the larger. Repeating this step recursively, so for T minus 2, T minus 3, etc., we obtain Z little t, and every time little t is equal to H of M at the terminal time capital T, given F little t, which is equal, of course, by definition, Z capital T, given F little t, for all t in our time index set. From this it follows, using the Tower law, this is just the Tower law, and from this expression above it follows in fact, this is not using the Tower law, this is directly using the expression above and then applying the Tower law. So in the first step we use the expression above at time t plus 1, the second step the Tower law, the third step the expression above, but this time at time t. This is true for all times, and thus Z is a martingale. Well, that is the martingale property, and we already proved the properties of being adapted and being integrable. In the second part of this question, we want to calculate the Snell envelope in a given very particular example. We saw in A that zt is equal to h of m at the terminal time capital T given ft at all times. Plugging this in, or plugging in the given values of h and m, we can expand the sum and use linearity of conditional expectation. On the left hand side, all the squares. On the right hand side, all the elements multiplied together which are not at the same time. Some of these are measurable with respect to ft. In fact, that's all yt's up to time ft. So their conditional expectation is just equal to those random variables. And it's the same for I not equal j, both less than or equal t. And the others, since the y's are all independent of one another, when they're conditioned on ft, nothing changes. They're independent of that, so it's just equal to the expectations without the conditioning. Since the yi are standard normal, the expectation of yi squared is equal to 1, and the expectation of yij is equal to 0 for I not equal to j, because they're independent and they have 0 mean. Therefore, this sum is equal to 1 multiplied by t minus t plus 1. This sum is equal to 0. So actually it should be t minus t. Because it's including t plus 1, the total length is capital T minus little t, plus 0, plus, and then the remainder, well, we have this sum, I equals 1 to t, of the yi squareds and the yi's and the yj's. This we can combine these sums again to doing exactly the reverse of what we did before, and get that this is equal to the square of the sum of the yi's. Right, nothing more than just the arithmetic of what we did before, which conveniently is equal to h applied to m at time little t. That then is a finished expression of the Snell envelope in this example.